Okay, uh, we're still in chapter 14 talking about buffers, but I wanted to introduce you to the rules of equilibrium before I demonstrate to you that the Ka times the Kb is equal to Kw. And this will be useful looking forward to chapter 15 and 16, and I might just link back to this video. So there's three rules of equilibrium. One is the inverse or the reciprocal rule. And what this states is if you have a chemical reaction like so, okay, and let's say the K equilibrium value for this is 50, and you want to know what the equilibrium is for the inverse, okay? So you basically flip the products and the reactants around. The equilibrium constant here is going to be 1 over 50. And you might be thinking, what? How does that work? Well, remember that this is products over reactants, okay? And this is products over reactants, okay? And, you know, A over B, that ratio is 1 over B over A, okay? So B over A is 50, the original equilibrium constant, okay? And then if you flip things around, shown here, I don't know, in a red box, okay? So if you invert the equation, the chemical reaction, now it's going to be A over B, okay? A over B. And basically, we want to calculate what that ratio is. So it's 1 over 50, okay? So let's look at an example here so you can get a feel for this. Let's look at an actual chemical equilibrium. SOCl2, whoa, this is a crazy looking record. Okay, SO2Cl2 gas is in equilibrium with SO2 and chlorine, okay? And the K for this is 2.99 times 10 to the minus 7. And I want to know what is K for this chemical reaction. Okay, and basically what we do is the K is going to be equal to 1 over the given equilibrium constant because we've flipped or inverted the chemical reaction. So we take the reciprocal. So it's going to be 1 over 2.99 times 10 to the minus 7. Remember again, equilibrium constants are unitless. So let's punch this into our calculator, and I get 3.3 times 10 to the positive 6, I think it was. 1, 2, 3, 4, 5, 6, 6. Okay. Okay. So that's the equilibrium for this inverted reaction. Okay. So it's quite simple. You take the inverse. Inverse means 1 over x, right? So if you're given x, you calculate 1 over x. All right. Let me give you a problem to do here so that I can make sure you understand it. Given this guy here, this is acetic acid ionization to produce acetate and hydrogen ion. So the equilibrium constant for this is 1.8 times 10 to the minus 5. So what is the equilibrium constant for the reverse reaction? Okay, and you'll enter that into your worksheet. All right. Rule number 2 is all about combining reactions. And basically, the way this works is if you have two chemical equilibria, like A is in equilibrium with C, and we'll just call these 1 and 2. So this is reaction 1, and let's say this has an equilibrium constant of 25. And then we know that C is in equilibrium with maybe D and E, okay? And let's say these are all gases, okay? And let's say K2 is, 100, okay? And if we want to add or combine these two chemical reactions, we add all of the reactants, okay? So A and 2C is in equilibrium with, and we add all of the products, C plus D plus E. What we do is multiply the two equilibrium constants. So the equilibrium constant for this combined reaction is K1 times K2, and so that would be, 25 times 100, 2500. Now I do want to mention that sometimes you can simplify the reaction. In this case, we want to do that. There's 2C on the left and 1C on the right, so we want to subtract 1C from both sides of this chemical equation to simplify the chemical reaction. Equilibrium is still going to be this value here, but we would have A plus C is in equilibrium with D and E. Okay? So if you add two chemical reactions, you multiply the two equilibrium constants. Okay? And we'll look at a practice problem later. So let me go to the third rule, and this is the coefficient rule. So for example, if you have a chemical reaction like so, okay, and let's just say this is K1, okay, and we want to know, hey, what if we multiply this whole chemical reaction by 2, and we have 2 A's in equilibrium with 2 B's, okay? What is this value going to be? Okay, what is this going to be? Is it going to be twice? Is it going to be something else? Okay, so remember that K1 is related to the coefficients of the balanced chemical equation. So there's a 1 here and there's a 1 here. So K1 is equal to B to the first power over A to the first power. And down here we have a 2 and a 2. So this is going to be equal to B squared over A squared. So you can see all of these 1's change to a 2, so it's squared. So K2 is equal to K1 squared, okay? So what this means is that if you have a chemical equation like this, nitrogen, hydrogen, ammonia, and we know the K value for this is 5.3, 10 to minus 5. What is K? 4, and we'll just multiply everything by 3. So 3 times 1 is 3. 3 times 3 is 9. 3 times 2 is 6. Okay, and what I want to do is notice that, everything's changing by timesing by 3. So what I want to do is take my my 3 and use that as a power to operate on the original Kp value given. Okay, and what I would do is 5.3, 10 to the minus 5, and you can multiply by that same number 3 times, or you could find your cubed button if you've got one in your calculator. That's 1.5 times 10 to the minus 13. Okay, and we'll do some practice problems here just to demonstrate these. Okay, so what does this actually look like when you get a problem? So here's what you might encounter. So question 17 says, given the following reactions and their equilibrium constants. Okay, so there's reaction 1, reaction 2. Calculate K for this reaction. Okay, and it looks like we need to modify some things to make them work out. Okay, so first what you want to do is look for the position of reactants and products. Okay, so we've got water on the left, and we've got water on the left, and we've got hydrogen on the right, and we've got hydrogen on the right. So I don't think I need to change the first chemical equilibrium any. Now for the second chemical reaction, there seems to be a problem because iron's on the right but iron's on the left. And then if we look at iron oxide, it's on the opposite side. So I'm going to switch K2. Okay, so I'm going to take this guy here and apply the inverse rule. I'm going to switch these around. So I'm going to write that out. This is the inverse rule. Okay, and that's in equilibrium with iron oxide, iron 2 oxide, and carbon monoxide. Okay, and the K for this, I'm just going to write 3 so I can have a different number here. That's going to be 1 over 0.67. Okay, and I'll do that on my calculator just to get a value. That's 1.49. Okay, I'll round it off to 266. All right, now let's think about, so iron's on the left, and iron oxide's on the right and right. So we're good. Now it looks like if we add these two chemical equations together, we will get the correct reaction. So I'm going to write out K1 here again in green, so there's no change here. And this is, I'm just copying this down. So I have 1.6. Now what I've noticed is that if I add these two equations together, I'll get water and iron, both on the left, and I'll get iron oxide and hydrogen, both on the right. Okay, so let me go ahead and do that. Let me use different color ink here. So let's write all this out. So iron. So when you add two chemical equations, you put all of the reactants for both chemical equations all on the left. Okay, even if you have a solid or a liquid, you would have to include that because it's part of the balanced chemical equation. And all of your products go on the right. So sometimes it's hard to fit it all in there in the space allocated. Okay, and what you'll notice here is that we can simplify it, and I think I simplified it in red last time. There's some terms that occur. There's a CO gas and a CO gas. There's one here and one here, so we can subtract one CO gas from each side. Just kind of like math, and that goes away, right? Same thing with CO2. We can subtract a CO2, and that goes away. And the result of your simplified equation is, this one right here. We got iron, which is a solid. Doesn't matter if that enters into the equilibrium expression or not. It's a part of the balanced chemical equation, right? And FeO, solid, and H2 gas. Okay, now what is the equilibrium expression for this guy here? Now remember, what you can do is use the product rule, okay? So we're applying the product rule now here. The KEQ for this balanced simplified chemical reaction is going to be equal to K3 times K1, which is 1.5 times 1.6. And let's get an actual number here on our nice calculator. It's 2.4. Okay? So that's how you do that problem there. Okay? You have to analyze things, see which one needs to be switched. Maybe you need to add two things. In this example, we didn't have to multiply anything by a common factor, okay? If, for example, one of these was 2 COs and one of these was 1 CO, up above here, I might have to multiply one of these reactions by 2 and one of them by 3 or whatever to get the number of carbon monoxides to cancel out at the end to give us the simplified equation. If I had to multiply reaction 1 by a coefficient of 2, I would have to square that, okay? But I didn't have to use that rule. All right. Here's your problem. Okay, try this one. So given the following equilibria, we have 2 NO and nitrogen and oxygen, and we have the K here. And we have NO and bromine and 2 NOBr, and we have the K here. And it says calculate KEQ for the formation of 1 mole of NOBr from its elements. Okay, so basically we want to take nitrogen, I don't know how many, 1, 2, 3, 4, 5. We want to take oxygen, I don't know how many, 1, 2, 3, 4, 5. And we want to form NOBr. Okay, and again, I don't know about the balanced chemical equation here, but I'm sorry, bromine is an element, not the oxygen. Oh wait, yes, that is oxygen. Let me clean this up. I'm kind of hyper here with my shaking hands. So we want to know nitrogen, oxygen, bromine, that's a Z. That's in equilibrium with, I'll use NOBr. Okay. And so we just want to get all of these on one side of the equation, that on the other side of the equation, and we will then be able to calculate the KEQ for this. Okay. And you can enter that into your worksheet when you're done working through this video.